So this is the framework that we've been looking at so far. We've been going from equations to an augmented matrix to the reduced to echelon form of that matrix to either the general solution or the parametric vector form. And the layer that we want to put on top of this is we want to think of vector equations and matrix equations as expressing linear combinations of vectors. So leading into our vector equations and matrix equations, we could have questions about linear combinations. So linear combinations might lead us to looking at matrix equations and vector equations. And then that will go to an augmented matrix if we're dealing with an equation, to a reduced to echelon form, to a parametric vector form. The parametric vector form is the linear combination form of the solutions. So when we're looking at the parametric vector form, we're looking at linear combinations of vectors. I should say that part. All right. So sometimes we want to ask questions about linear combinations, and we don't have an associated equation. We could take linear combinations of vectors, put them into a matrix, and send that to the reduced echelon form, and then use the reduced echelon form to read the pivots. Unless we're going to write down solutions, the general solution or the parametric vector form, which is a linear combination, we could just take the reduced echelon form, drop out at this level, and read the pivots. So if we just need to know if an equation is consistent or inconsistent, and if it's consistent, if it has a unique solution or many solutions, we can just drop out of the reduced echelon form and read the pivots. So that's what we want to talk about today. We want to talk about just reading the pivots. And this is what we focused on in section 1.5 and 1.7. So reading the pivots. Here are some important conclusions. Let's let A be an m by n matrix. Yeah, that's fine. Let's let A be an m by n matrix. So let's just start talking about a matrix. This is not an augmented matrix. If I wanted this to be an augmented matrix, I probably would not have given it a name, and I would have stated that it's an augmented matrix. So since I did not state it's an augmented matrix, it is not an augmented matrix. Not an augmented matrix. Usually we don't name augmented matrices, we name the coefficient matrix. And if I want a matrix to be an augmented matrix, if I want you to read it that way, I have to tell you to read it that way, or I have to open up with an equation or a system. So let's let A be an m by n matrix. We want to read where A has pivots. One of the things that we saw yesterday is that if A has a pivot in every row, this is the coefficient matrix, if A has a pivot in every row, then the equation AX equals B will be consistent for all choices of B in Rm. So first thing to notice, if A has a pivot in each row, if A has a pivot in each row, then the equation AX equals B is consistent for all B in Rm. If A has a pivot in each row, then AX equals B is consistent for all B in Rm. And we talked about why that is. This is because the augmented matrix, if we have a pivot in every row of the coefficient matrix, there's no room to have a pivot in the rightmost column of the augmented matrix. So the reason that this is, the augmented matrix where I have the coefficient matrix and I put the B over here, could not have a pivot in its rightmost column because I filled up all the pivots in the coefficient matrix. The augmented matrix cannot have a pivot in its rightmost column. So the reason that if A has a pivot in each row, the equation AX equals B is consistent for all B in Rm is that the augmented matrix A, B cannot have a pivot in its rightmost column because all the pivots are here. So we won't get a pivot in the rightmost column. So when we say that AX equals B is consistent for all B in Rm, we're using equation language because we're talking about an equation and being consistent. Another way we can say that is that the columns of A span Rm. So let's switch pages. Another way we can say that is that the columns of A span Rm. So that is, oops, I spelled that wrong. So if A has a pivot in each row, then the columns of A span Rm. Every vector B in Rm is a linear combination of the columns of A. That is, every vector B in Rm, that's supposed to be an M, in Rm is a linear combination of the columns of A. So these are all things that we conclude because A has a pivot in each row. So when A has a pivot in each row, that means the equation AX equals B is definitely consistent for all B in Rm. That means that the columns of A span Rm. And that means that every vector B is a linear combination of the columns of A. And then we're going to include with that, today we're going to talk about linear transformations. And that would mean that the transformation, that's going to be the new thing that we read about. The linear transformation that maps Rn to Rm given by T of X equals Ax is surjective. So that means T maps Rn onto Rm. Get it here. So these are all things that we'll say when we see that A has a pivot in every row. Pivot in every row, columns span Rm, and the equation Ax equals b is always consistent, and the linear transformation given by multiplication by this matrix will be onto or surjective. So this is what we're talking about when we're reading the pivots. We want to make sure that all these things go together. We want to make sure that we don't say something like A is surjective. That, I understand what you're trying to say, but that's not how we would say that. We wouldn't want to say that the transformation spans. I understand what you're trying to say, but that's not how we say that. It gets the point across in not a very clear way. Those aren't the things that go together. It would be like saying we piloted our car. That's not how we say it unless we're an automotive journalist and we're trying to sound fancy. You're not piloting the car, you're driving the car. Similarly, we wouldn't say that we're driving the plane. It sounds like you don't know what you're talking about. So we got to be careful with how we make these associations. Any questions? Rad. So these are the things that we're going to conclude when A has a pivot in every row. This brings up the next question. What if A has a pivot in every column? So let's let A be an m by n matrix still. So A is an m by n matrix. Once again, not an augmented matrix, because it wouldn't just have a name. And I would have stated it's an augmented matrix. So if A has a pivot in each column, if A has a pivot in each column, then if the equation Ax equals b is consistent, then the solution is unique. So if A has a pivot in each column, and if Ax equals b is consistent, then the solution is unique. So a pivot in each column means that if the equation Ax equals b is consistent, then the solution is unique. This makes sense because if we think about the augmented matrix, no, an equation does not have to be consistent with if A has a pivot in each column. If there are too many rows, then A might not have, A can have a pivot in each column, but not have a pivot in each row. So this makes sense because if we imagine the augmented matrix Ax equal, for the equation Ax equals b, so if there's a pivot in each column of A, there are no free variables. A pivot in each column of A means the solution set has no free variables. A pivot in each column of A means the solution set has no free variables. So it's possible for A to have a pivot in each column, but still not have a pivot in each row. That's why we need to qualify this by saying if Ax equals b is consistent, then the solution is unique because there are no free variables in the solution set. So this is the language that we're using. We're looking at a pivot in each column of a coefficient matrix, and we're making a conclusion about an equation. We also can draw a conclusion about the columns of A. So if this consistent equation has unique solutions, because there are no free variables in the solution set, that means that the columns of A are linearly independent. That is, the columns of A are linearly independent. Because there are no free variables, because every column of A is a pivot column, that means one of the columns is not a linear combination of the others. So one of the columns could not be a linear combination of the others. So in a sense, we need all the columns of A to describe everything that A can describe. Any questions? So that's a statement that we're making about the columns of A as a set of vectors. Linear independence is a thing that we describe a set of vectors with. And there's going to be a transformation description as well. The linear transformation that maps Rn to Rm will be what's called injective or one-to-one. So that's adding the new thing today. That is the linear transformation. T maps Rn to Rm given by T of x equals Ax is injective. Or we could say that T is 1 to 1. All right, so that's a statement that we can make based on the transformation associated with the matrix. So we have two places we're looking for pivots, a pivot in each row and a pivot in each column. In each of those cases, we're drawing a conclusion about an equation, the columns of the matrix as a set of vectors, and the linear transformation associated with the matrix. Any questions? It only seems like it's a lot to remember because it's a lot to remember. And you have to remember all of it, all the time, and perfectly. Any questions? Yes, question? So the vector equation just looks like the columns of A with weights in front of them. So that the vector equation is x1 v1 plus x2 v2 and so on. All right. When we talk about the matrix equation Ax equals b, the reason that we want this matrix equation is because it's a more compact version of the vector equation. But we want to think of the A times x as that linear combination of the columns of A with the entries in x as weights. So it's a nice compact form of the vector equation. All right, let's pause the video here and switch over to doing some examples.